So here we have the ALU. So it is ALU underscore 4 is the name of the entity, because we have 4-bit inputs which we are dealing with. So A and B are 4 bits, and there is one F which is also the input, and it's 3-bit input. So it's like 2 down to 0. And then we have an output which is also 4 bits, but we have the C underscore B, which is a single bit. So it's like standard underscore logic, but for all others we have standard logic vector, and then the size, whatever it is. And this is the mode. This is the input mode. Like we are taking it as input mode. It can be output mode. It can be in out mode. So here we have only used in and we have used out. It can be in out as well, which is basically the bidirectional way. Then we have the library, which is IEEE, and then from that we are trying to include standard logic 1164. So what's this? This is basically that inside this library we have the package that is standard logic 1164, and from this we have like all these data types that we are trying to use, that is standard logic vector, and then the standard logic. They all come from there. Basically you can see this thing, I have created it from ChatGPT. So whatever after I explain this code, you will be able to understand that the logical operations that we are trying to carry out, or the concatenation operator, and the signal types, as I told over here, the standard logic and standard logic vector. Standard logic and standard logic is this one, and standard logic vector is this one for a multi-bit. All of that is coming, like the definitions for all of these, it is coming from the from this package which is inside the IEEE library. Since VHDL is the IEEE standard, we all know that. And so this is the entity part. Entity basically explains what are the inputs and what are the outputs for a particular block. So we can see over here like very clearly that A, B, F, these three are the inputs, and Y and C underscore B are the outputs. So A represents the 4-bit input A, B represents the 4-bit input B, F represents the function. So we need to basically carry out logical and arithmetic operations as part of like this experiment. So like we have 3-bit, 2 down to 0 means 3 bits, 2, 1, 0. So the bit number 2, bit number 1, and bit number 0. So if we have like all the possible the combinations here, it can be from 0, 0, 0 up to 1, 1, 1. So we have 8 possible combinations. So 8 combinations are possible here. So what these 8 combinations are, 6 of them are logical, and then we have 2 arithmetic operations. That's what we are trying to achieve. So 6 logical operations which we are trying to basically do is AND, NAND, and NAND. Then we have OR, NOR. Then we have XOR, XNOR. So these are the 6 logical operations that we are trying to carry out. And then we have 2 arithmetic operations. So the arithmetic operations are plus and minus. We are not trying to implement divide and multiply. So divide and multiply are beyond the scope, so we will not discuss that. We will only discuss about these 8 operations that we are trying to carry out through the selection by this F. So depending on the value of F, we need to select the logical operation, which can be from like either logical or it can be arithmetic. Then we have the C underscore B. So this basically indicates carry and borrow. It's basically carry or borrow. So this part is basically relevant only when you are trying to so this is only relevant when you are trying to go with the arithmetic operation. For the logical operation, it's not even like we don't even need to look towards it. So we basically keep it 0. So in order to keep it 0, we have to do the concatenation of 0 with whatever operation we have carried out. So suppose we have carried out AND operation over here, A and B. So after doing this operation, you have to just add a 0, which is basically stored in this signal, that is the result. So result is a 5-bit which we have declared inside the architecture declaration section. So this is the architecture declaration section where we have declared the signal result. It's a 5-bit signal. So basically signal, name of signal, colon, data type, standard logic vector, and then the size. So if it would have been a single bit, it would have been standard logic, and this part it would not have been there. But since it's a multi-bit, we need to keep it like that. And now you would be thinking why it's a 5-bit signal. So basically the 5th bit, so basically y. So the means of assigning the output to y is like one of the way which you can think is, why are we not directly using y over here? Okay, that would actually be wrong, because what happens is when we try to synthesize that, then it will lead to problems. So what happens is, as I had done in case of, as I had actually encountered that issue, I had put y over here directly. So it basically like has the issue that it will actually consider multiple drivers for the output port, but incorrect that's incorrect. So in order to resolve this issue, even if we keep it inside the process, so as we know that in case of process, it will, if instead of like this result, we had y over here everywhere, so if I just replace y over here, here, as well as everywhere, like wherever this result is used, instead of that, if I use y directly, then what would have happened differently is that that we are trying to, actually the synthesis tool will give this error. So synthesis tool will raise an alarm of how you're trying to do that. But for the internal signal which we are trying to define over here, that is the result, it will not have any kind of issue like that. It will allow that to happen smoothly. So that's why we are trying to declare another variable result, which is basically coming over here in the architecture declaration section. So the 5th bit, which is the like the 4th bit, like we have the 0th bit, 1st bit, 2nd bit, 3rd bit, 4th bit. So the MSB bit or the 4th bit will be assigned to C underscore B, which we have done over here. Results 4th bit is being assigned to C underscore B, and the 3 bits or the 4 bits are being assigned to Y. So this is outside this process. So this and this entire process, whatever is written inside it, all of that will be executed like in the concurrent nature. So whatever is written inside the process clause will be executed in concurrence. So the process, the assignment of the MSB bit to the C underscore B output, and the assignment of 3 down to 0 bits of result signal will all happen in the concurrence. So this is what is happening. And now what is happening is that like you just wonder over here why we have done this ending after. So first we carry out the operation, and just to not leave that C underscore B bit which will be assigned at this stage floating when we are trying to carry out a logical operation, just to not leave it floating, we are trying to put it 0 over here after this operation has been carried out. So the 0 will go on to the C underscore B, and the Y will be assigned the result of the ending. Whatever is the result of the ending, that will be assigned to Y. So that's how this is working. So basically case will so f, so this value f, whatever is the value of f, that is the function which you are trying to select, it can be logical or it can be arithmetic. So 6 logical and 2 arithmetics operation. So when f is 0 0 0, what we intend to do is an AND operation. When it is 0 0 1, we want to do an AND operation. So case like on this signal, on this input signal is, and then when clause, when this, so this, so this f, whatever value it has, accordingly that will be selected out of this. So this, or this, or this, or this, or this. So any of this, which whatever one it has, that will be selected. Now one question might come that why have we not like taken 111 over here directly. So basically the synthesis will raise issues when we if we do not put this when other statement. So instead of putting a 111, like when and then in quotes 111, this could have been done like this, right? When 111, do this. But instead of that, we are just putting others. So it will take care of all other scenarios. See, the value may not always be zeros and ones. It can be unknown, and it can be floating as well. So we don't need any issues with this synthesis tool doesn't want any issues to be happening in our design. So that's why it will have the more preference for putting others instead of 111 over here. So these are the logical operations, and then the two arithmetic operations, which is the addition. First is the addition. So in case of addition, you observe over here, we are first extending this a, yani ki x a was originally 4 bits in size. We have extended it to 5 bits by adding a 0 in front of it. Then we have also extended b, and after doing the extension of a and b, we have carried out the addition operation. So this is the difference. This is quite a difference. Like what we were doing over here, we were doing the concatenation, which is ANDing with 0. Like it's not actually ANDing, it's basically the concatenation. So we are doing the concatenation after this XOR has been happened. So like suppose if we have 1011 for A, and we have, let me take a very easy example, 111, and we have 000. So our XOR result of this would be 111, obviously, since like it will be like any one of the bit is high, output will be high. So this 0 will be added after this operation has been carried out. If it would have been like this, that is like we are first doing 0 and A in one bracket, 0 and A in one bracket, and then XOR with 0 and B. But we are not actually doing that. We are carrying out the operation first, and then we are adding a 0 in front of it. This is for the C underscore B. That will be kept 0 for all the logical operations. So this is how it is happening. Similarly, if we observe over here that for the addition part I explained you, for the subtraction part there's a slight trick. What happens is that when you're trying to subtract, say 6 with 3, it's a simple thing, right? It will give you a positive 3, but in case of the other case where we have 3 minus 6, that would be giving a minus 3. So in the case of subtraction, you can have two possible cases. One is that the result is positive, the other is that the result is negative. So how do you actually handle this? In RTL code. So what we are doing is we are trying to do two possible implementations of the subtraction operation. So in case if A is less than B, that is this case, what we have to do is that first we have to extend it, that is the first thing, to 5 bits. So now the A would be 5 bits with the MSB bit 0. Then we have to also do the extending of the fifth of the B, right? But there is a catch. You would observe that they have done a NOT operation over here on B before we have extended it. So what this basically means is that we have taken the 2's complement of B. So this part is basically 2's complement of B. Why? Because we have extended it after taking a NOT and adding 1. So when we are, so suppose 2's complement means 1's complement plus 1. So 2's complement is equal to 1's complement plus 1. It's a standard rule. So 1's complement basically means invert all the bits. And that's exactly what we are trying to do. Invert all the bits. This is exactly what we are trying to do over here. And then we are extending it by 1, or extending it by 1 bit, which is the 0, which is the MSB bit. And then we are trying to add 1 to it. So if you observe over here clearly, so this bracket just segregate it out to make it more clearer, right? So if you observe that this bracket is being highlighted, that means that first this NOT operation is being carried out, then you have the extending, then you have the addition of 1. These are the 3 stages. And what this will do is it will create a 2's complement of B. After creation of 2's complement, what happens is that if we need a -3, that will, so basically in the computer you cannot store negative number. So what happens is that numbers will be stored in 2's complement form. So when we are doing this operation, actually we have found the result. After carrying out this operation, we have found the result, but there is a issue, there is a catch, and the catch is that the result of this thing, which is basically till here, I can say, just one second, yeah, till here, you see the highlighted brackets over here, from here to here. What we are trying to do is A and then 2's complement of B. That is basically giving us a result that will be storing the -3 in 2's complement form. So that is not so that's not actually what we want. In order for us to understand, we need to again take the 2's complement. So for taking the 2's complement, we are doing a NOT plus 1. So NOT of this entire thing. So the NOT of this entire thing, what we are taking over here, from here up till here, right? From here up to here, we are taking it like the whole thing from here. We are doing a NOT and we are adding 1, what we did over here for B. So this will give us the 2's complement of the result. So what happened is that after doing 3 minus 6, basically we did 3 plus minus 6. What this basically means is we took the 2's complement of the B. Suppose 6 is B, so we have taken the 2's complement, which basically means -6, okay, and then we have added it to 3. We have added it to 3. 3 is like A, okay. Then after getting this result, the computer cannot store the negative value, so it will store it in 2's complement. So it will not be actually -3, it will be 2's complement form. So we have to take again the 2's complement, okay, and then after taking the 2's complement, which is taking the NOT and then adding 1, we actually get the result. So that's what's actually happening over here. It just took some time to explain, and the same process, exact same ditto process is happening over here. But the catch is that we are not doing a NOT and a +1. If we just replace this thing, okay, this thing with this thing, okay, if you just replace this thing and this thing, it's exactly same, this line and this line, but the only difference is that we don't have to take a 2's complement at the end because the number is positive, okay. So as I explained you that why we are trying to include these packages is because of this reason. Like the logical operations, we need the standard logic 1164 library. Oh, sorry, we need like this package from the IEEE library. For the concatenation operator, we need standard logic 1164. For this, for like the signal type, which is the standard logic vector, we need this this particular library. For carrying out the comparison operator or the arithmetic, which we are doing over here. So this is the arithmetic part. I told you over here, this is the arithmetic. So this is a plus, this is a minus. So this arithmetic and the comparison, A less than B, this part. So that will be basically covered under this library, standard logic unsigned.oil. Okay. So this is the comprehensive explanation of the main VHDL module, and I hope you understood it. And now let's move towards the test bench. So before I forget, what's actually happening here is that when we are trying to create, say I go to this, I have created the project already. I am going in the implementation mode. I want to add a new source, say a Verilog VHDL module, obviously, and then we have a ALU_4_explain. Just for explanation I am putting it, so let's put it like that. When I am trying to select the signals, I again select A, which is the input bus 3 down to 0, input B 3 down to 0, this is B, Then we have the F, which is input, which is nothing but 2 down to 0. This is 2 down to 0, 3-bit input, right? Then we have the C underscore B and Y, which are the two outputs. So we have a Y, we have a C underscore B. So this is out, 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 okay, and this Y is basically a bus. So we need to select this bus thing, 3 underscore 0. So basically it will give a 4-bit thing, right? So we are all done. Let me just change the name of the architecture. So you can change the name of architecture directly over here. Okay, explain underscore R. So whatever name you have given, entity name, don't put explain, just put ALU underscore 4 underscore R. Since I already have that file, I'm not creating it again, just for explanation part. Okay, now I'll remove this afterwards, so just don't worry about that. So we get this code which is generated, so we just need to remove this comments part. Okay, then we have standard logic, this thing. So we have this library, but make sure that you include the other library, standard logic unsigned dot all. So this is not already there, so this we have to actually put up over here. So this is what we get. We only get this much part. This additionally I have put. Okay, remove all the green parts from this thing. Okay, as usual. So this is this. So you get this entity thing made up already. Architecture is also made up, like the basic definition. Now what I have to do over here is I have to add this signal result standard logic 4 down to 0 between the architecture and architecture's begin. So it will go into the architecture declaration section. Then this process, and then this case, and then all this if else and case and process and all those things. That and this Y is assigned the result 3 down to 0, and then C underscore B is assigned the result, the 4th bit of result. So all these things have to be written between begin and end. So this is what I have to write, and this is what the tool generates. So I hope you understood it. So this is very quite easy and clear. Thank you.